Two capacities. There's a couple of reasons we're running this today. There definitely seems to be a level of frustration in the industry. I get people every now and again talking to me saying things along the lines of why are these capacities so damn useless? And in addition to that, something that's come out of your mouth perhaps before. And in addition to that, there is most definitely a spectrum of understanding on this topic. For most of us who've had some design experience, anchors are really a niche within what we do. But there is actually quite a depth of understanding that comes in this area. C2 capacities aren't magic numbers. They represent something fairly specific that is often communicated fairly poorly. And so the intent here today is to give you a little bit of background on what these values actually really represent. I've got probably about 40 minutes, and so we should have lots of time for questions at the end. Largely split into three sections. We'll go into a little bit around where these capacities come from and why they exist in the first place. And then we'll do a bit of a deep dive into the testing behind them. And this is just to give you a real understanding of what they actually represent. And then we'll go over some of the ambiguities that exist in this space so that you're, as a designer, conscious of them when you're using these capacities in design. So this whole part of our industry really kicked off in 1994 after the Northridge Earthquake in California. Prior to this, designers were using monotonic test data in uncracked concrete to design post-installed anchors. I suspect everyone in this room will intuit that this is going to be unconservative in many seismic scenarios, and there were many failures in this earthquake of post-installed anchors. This triggered a lot of work in this space. This is a timeline from that point. There was initially a 2-year ban completely on post-installed anchors for seismic applications in concrete in the US. This mainly affected the West Coast, so your California, Oregon, Washington states. There was a lot of research in this period, but the first performance testing criteria wasn't actually published until 2001, which was the ACI 355 guidelines. It wasn't until 2013 when the Europeans came to the party and published what we're mostly familiar with in New Zealand, those kind of C1, C2 guidelines. C1 is really heavily based off the ACI 355 guidelines. They really took that and they added this C2 criteria above that for higher levels of seismic loading. Now, in 2016, Annex E, which is the criteria for C1 and C2, was actually technically superseded. The correct reference is now Technical Report 049. It is essentially the same document. They just restructured how they did their codes, but it's a good thing to be aware of. 2017, this is when New Zealand came to the party, right? Amendment 3, and this is when we started using C1 and C2 capacities in our designs. I think it's interesting to note that this is not where it ends. So this is still very much a developing part of our industry. In 2020, the International Code Committee released their acceptance criteria for post-installed anchors in cracked concrete under seismic loading. ICC, for anyone who's not particularly familiar, is the independent code assessment organization primarily in the US, or they do work in other countries as well. And then, very interestingly, last year the ACI 355 committee actually proposed a full adoption of the C1 and C2 performance categories in the US. So what we're seeing is this becoming a worldwide system, right? It really is here to stay. That being said, it very much is still a developing part of our industry, and if we look back in 10 years, I'll be very surprised if we're doing things the same way as we're doing them now. Now, I suspect everyone here has seen this clause before, right? This is straight out of 3101. This is why we use C1 and C2 capacities. Post-installed mechanical anchors and post-installed adhesive anchors shall pass the pre-qualification testing stipulated in ETAG 001 Annex E and be designed in accordance with EOTA Technical Report 045. Two quick notes on this. Both of those documents are technically superseded. The correct ones are down below. Again, the actual impact of this is fairly small, but it's worth knowing so that when you see this on supplier data, those ones are actually correct and from a design point of view are the ones you want to see on documents. Now, this is with regards to what capacities you should be using. This is straight out of Eurocode. Whether or not we look at using a C1 or a C2 capacity is a function of importance level and the seismicity of the area. The Eurocode important classes actually align quite closely to ours in 1170, and for scenarios like this, we can take them as a one-for-one. A little bit of work has to be done to match our accelerations, but it's not too difficult. And really in New Zealand, we're largely talking about ground accelerations greater than 0.1 g, and so the vast majority of cases that most of us in this room are looking at, we're going to be using C2 capacities. That's a little bit about why we're here in the first place. This is going to be a bit of a deep dive into some of the testing procedures. The intent here is not for you to be able to go away and run a test program. Right, the intent here is to give you the level of information that is going to be useful and interesting as a designer so that you have some context for the values that you're using in your design. Now, when we talk about post-natal anchors in concrete under seismic loadings, there's two things we care about, broadly speaking. There is the fact that the concrete cracks, right? Reinforced concrete, this is pretty well understood. When you're to engage a reinforcing, you require cracking for that reinforcing to engage. This means you have cracks in your concrete. When the cracks occur where the anchor is, right, take it to an extreme example, your anchor is going to fall out. But those moderate examples do impact anchor performance as well. The larger the crack, the less capacity that anchor is going to have fundamentally. The other aspects to seismic loading is, of course, what the anchor actually experiences. And so these are those loading protocols on the anchor, and that, broadly speaking, is what C2 is trying to capture. With regards to the cracks specifically, I've got two screenshots here from different test programs, both done in the early 2000s in California. The one on the left is looking at crack behavior in a reinforced concrete slab. The intent behind this research was to quantify the probability of when cracking occurs in a reinforced concrete member, what is the likelihood that that crack occurs where the anchor is? And the conclusion is that very commonly. The reason is your anchor acts as a bit of a stress raise, right? It's a slight weak point in the slab. So when cracking does start initiating, there is a more than likely chance, not 100% chance, but it's more than likely that that crack occurs where your anchor is. And so there is a fundamental assumption in all of C2 that we're allowing for that to happen. Right? These C2 capacities allow for the fact that that crack, it assumes that that crack is going to occur where your anchor is. The image on the right is from a different study, although one of the authors is the same. This is looking at the crack widths that we allow for. Now, there are two crack widths of note, and you're going to be sick of me saying these numbers by the end of the presentation, I'm afraid. But there's a 0.5 crack width, and there is a 0.8 crack width. 0.5, these are millimeters. 0.5 mils is intended to represent service conditions and light seismic loading. And this is best represented by a C1 capacity. The 0.8 crack is meant to represent the scenario where you just start getting yielding of your reinforcing in a concrete beam. And this is meant to represent a high seismic loading scenario. Fundamentally, these are the crack widths we're allowing for. A C2 capacity is allowing for a 0.8 millimeter wide crack. One thing that is worth noting is these crack widths were developed thinking about the elastic portion of a beam. Right? The plastic hinge zone is absolutely not covered by a C2 capacity. In a seismic event, we expect pretty severe cracking and damage in a plastic hinge zone, and there is no anchor, to the best of my knowledge, that is at all in any way rated to be used in a plastic hinge zone under a serious seismic loading. Now, with regards to the loading protocols, right, there's three that we take into consideration with regards to, or when we're developing a C2 capacity. The first is cyclic shear, and I hope you really enjoy my fantastic animations. Right, we put a new lateral system into a wall. The wall is loaded in plane. Our anchors are going to be acting in cyclic shear. It's well understood. The next one is cyclic tension. Say we have strong backs in a wall, that wall's loaded out of plane cyclically in an earthquake, there's going to be cyclic tension in those anchors. The third one, I think, is the most interesting. Cyclic crack widths. So say we have an anchor in a reinforced concrete beam, and that beam is part of a concrete moment frame. That beam is going to undergo moment reversal on every cycle of the earthquake, and the cracks on the underside of that beam are going to both open and close. And so this is something that's allowed for in a C2 capacity. This is really important because when an anchor opens, the width of the anchor affects the capacity, but it also is a problem when the cracks close because it starts crushing the concrete around the anchor. So this is a mechanism that C2 also takes into account. One quick note, the cyclic shear, all my animations are going to be in that direction, but all the shear really should be into the page, into the crack. That's just a reflection of my limited animation ability, not anything else. Okay, I'm going to be very insulting to anyone who's done testing in this space. The test procedure you run to develop a C2 capacity is hundreds of pages thick. But the tension capacity kind of comes just down to this formula. And so we're going to go through in a little bit of a detail. On the right-hand side, you have the baseline kind of starting capacity you start with. This is simply the tension capacity of the anchor in a crack that is 0.5 mils wide. This is that 0.5 mil crack, right? It's intended to simulate surface level cracking or light seismic load cracking. There are a couple of other tests behind this that take into account things like variability in drill bit diameter and concrete strengths. But for the sake of this, just take it as your baseline capacity in a moderate crack under surface or light seismic loading conditions. We then reduce this baseline capacity by an alpha and beta factor. And these alpha and beta factors are the ones we apply to generate a C2 capacity, and these are the ones that take into account those crack loading scenarios and those loading scenarios on the anchor that we mentioned. Really, there are three tests. There is a monotonic test in a crack that is 0.8 mils wide, and right, so this is allowing for that larger crack width that we expect in a significant seismic event. And then these two on the right. First is cyclic tension. Oh, I think I have animations. First is cyclic tension, and then the next is cyclic shear. One thing to note that's quite important about, cyclic crack. One thing that's quite important to note about the cyclic crack test is throughout this test, there is a constant tension load maintained on the anchor. This is to simulate scenarios where, say you're in Auckland Hospital, whichever direction it is, and you've mounted an MRI machine to your beam, right? And you need to make sure that that MRI machine doesn't fall down and hurt anyone through an earthquake. So you need to be able to maintain that tension load throughout that earthquake. That's what that test is trying to simulate. Now, I have sketched down the bottom how the alpha factor gets built from these tests. We take the result of the monotonic test and we times it by the lesser of either the cyclic tension or the cyclic crack width. And there's a reason we don't superimpose them. The reason is, there's another study done in the early 2000s where they built a single degree of freedom reinforced concrete moment frame. They mounted some surfaces to the underside. They measured the tension load in the anchor over time, and they measured the width of the crack over time. They put it through thousands of cycles. The conclusion of that study was basically that there is no statistically significant relationship between the max tension load in the anchor and the max crack width. Now, don't worry if you didn't digest that entirely. The thing to take away from that is that makes sense and there's justification for it. If we delve a little bit deeper, and I really apologize for the amount of data and stuff on this slide, but bear with me for a moment and we'll get through the other side. If we look with a little bit more detail into each of these tests, this is the cyclic tension. The actual process is that vertical line running up and down is tension, right? So you're loading it in tension. You take your crack width to a certain crack width, at 0.5 crack width, you run lots of tension cycles. You continue to increase the crack width while that tension loading is going on, right? That is intended to simulate scenarios where you have the crack and you have the cyclic tension going on. Cyclic crack width, which I've already mentioned a little bit, so it looks very similar, but they've kind of flipped it. The cyclic line going up and down is the crack width, and the constant line is tension load. So you load it up in tension, you start cycling the crack around the anchor, and then you put more tension on it, and you continue to cycle the crack. The number of cycles at maximum crack width has a huge impact on anchor performance. The reason for this is you're not only opening the crack, but you're also crushing the concrete around the anchor every time you close the crack. And again, it's to simulate that moment reversal scenario in a concrete beam. Now, the results of these vary depending on the type of the type of anchor that you're using, a fair amount. But to give you all a sense of scale on the impact of these on the end result, it would be common for, say, a screw anchor in concrete to have a reduction factor for cyclic tension of around 0.9 and a reduction factor for the cyclic crack test of somewhere between 0.2 and 0.3. Overwhelmingly, the reason that C2 tension capacities are so low is from that second test. Right? The two functions that have the biggest impact is the width of the crack and the number of cycles, specifically the number of cycles at the largest crack width. It's because you're opening the crack around the anchor and then you're crushing the concrete around the anchor again, the whole while that the anchor is under constant tension load. Now, quickly on the beta factor. The beta factor is, a simplistic version would be to think about displacement, right? Your alpha factor is looking at loss and load carrying capacity for the scenarios we've talked about, and your beta factor is looking at displacement performance. You measure it at 2 points in all your tests, at the 0.5 crack width and at the 0.8 crack width. Again, you'll be sick of me saying this, the 0.5 crack width being service level conditions, the 0.8 crack width being heavy seismic loading. Now, in my experience, the actual impact of this on your end result is relatively small, but it does have limits built into the calculation. Now, what this does is it limits the absolute displacement of your anchors at service and extreme conditions, and it limits the spread of displacements. This is so that any anchor with a C2 capacity associated with it, you know, isn't going to have excessive displacements in the application that you're using it in. That's the intent behind this. Both excessive displacements or displacements that are hard to predict and variable. That's the two things that it's protecting against. Okay. The end result of this, so we have that initial capacity. It's a characteristic 5th percentile capacity. We do the two reduction factors to allow for the C2 loading protocols, and that gives us the C2 tension capacity. One quick note on this, you will see written in the supplier's documents C2 tension resistance. This is the Eurocode description. You can use them interchangeably in New Zealand. Okay, shear, you'll be thankful to hear, I'm going to go through shear in the same level of detail. It's much the same philosophy, right? You start with your base level shear capacity in a 0.5 crack representing service level conditions or light seismic loading. You then reduce it by the alpha and beta factor. There is one thing that is worth noting for shear testing. These are the tests that are run for C2. So you only have your monotonic test and your cyclic shear. You don't run the cyclic crack width test for shear. The reason for this is there was a study that basically came to the conclusion that the cyclic shear test is reliably worse than the crack width cycling one in shear. And so this just means they were able to remove one of the tests in shear and make the test program a little bit easier without really changing the outcome. But that is why. And there's a lovely animation that I hope you're all enjoying. Okay, One other quick thing to note, all cyclic shear testing, and this really should be how cyclic shear testing is always done, always is in the positive and negative positive and negative direction. It's very important that this is done. This is what best represents reality, and this is indeed how the C2 test program is built. Okay. Now, ambiguities. There's a few caveats that are worth noting here. It's really easy to pick apart other people's test programs and other people's standards. Putting something together like a C2 performance category test program is an immense amount of work. It requires an immense amount of research backing and is very, very difficult. So this is not at all a comment on any of that, but I think it is really important to be aware of the ambiguities in the systems as designers so that you're aware of what you're actually using when you get a C2 capacity. Because again, it's not a magic number, it does represent something specific. Crack widths. The 0.5 and the 0.8. There, to the best of my knowledge, and the best of the knowledge of anyone I've ever spoken to on the topic, there is no documented basis for the 0.5 crack width for service conditions and light seismic loading. It first appeared in 2006 when they published the ACI 355 guidelines. Maybe they did have justification, but it wasn't documented very well. Now, this is not to say that that is wrong or unreasonable. It's just to say that we don't have justification for it. The thing to keep in mind is when you're thinking about a C1 capacity, fundamentally what it's allowing for is a 0.5 crack width. Now, the 0.8 crack width, we do have documented justification for. The logic for that was that we should be rating anchors for the moment where a reinforced concrete beam reaches the stress where the reinforcing just starts to yield. And so they used empirical formulas to calculate the crack width at the stress that the reinforcing is about to yield. However, they used empirical formulas that were developed for or from testing and developed for beams under service stress levels. It is unclear how well these formulas extrapolate to extreme scenarios like reinforcing yielding, and so we're not entirely sure how precise that 0.8 is, or how reflective that 0.8 mil allowance is of reality. Now, that aside, fundamentally, what C2 testing is allowing for is a crack of 0.8 mils. That is fundamentally what we're testing and what gets provided, regardless of any ambiguities around where it came from. Okay, next ambiguity. You might have noticed I'm talking about reinforced concrete beams a lot. This is because all of the development of the crack widths was done on research on reinforced concrete beams. Now, I think we should maybe take a step back to first year university. We're going to go through a building system of a building. Beam, not beam. Also not a beam. Still not a beam. Definitely not a beam. This is not to say that it's wrong, but all of the background is based on beams. And so it is not necessarily the case that crack behavior in beams is reflective of things like shear walls or things like columns. Maybe it is. Fundamentally, we're allowing for that 0.5 and 0.8. That is fundamentally what that capacity represents. But I am not sure how well that represents other elements in a reinforced concrete structure. Okay, next one, crack cycles. You might remember when I was talking, you might have fallen asleep, there's a lot of information on the page, but when we were talking about tension capacity, I mentioned that largely, or overwhelmingly so, the reduction comes from that cyclic crack test. And in fact, overwhelmingly, from the last couple of cycles at maximum crack width. There is a number of cycles that is specified in the documents for C2 testing that you run when you run this testing. This is based off a 475-year return period earthquake in LA, specifically a 90th percentile 475-year earthquake in LA. There is no method for us to scale that, or for you to scale that in design, to any other return period of earthquake. Now, this arguably is less of a problem if you're looking at shorter design lives, because your capacity is conservative. You know it's conservative. That's fine. You have that in your mind in design. Fantastic. Where it really has implications for is if you're doing critical infrastructure, if you're looking at a hospital, if you really need your anchors to work in really large return period earthquakes, fundamentally, C2 is allowing for a 90th percentile 475-year return period earthquake in LA. And so that is a point of concern and something that I think is important to be aware of if you are looking at those critical infrastructure projects. Oh, lovely animation. Next one. Imagine for a second that this is a half reasonable sketch of a 2-story reinforced concrete frame building. And we have a service mounted to the beam, and that beam has been designed as a capacity protected beam because we're in New Zealand. Really, we don't expect really any seismically induced cracking in the capacity protected beam, right? What a C2 capacity is allowing for is that 0.8 crack. And the basis for that is assuming that you're reinforcing and your beam is yielding. Now, that's not to say you don't get any cracking in a capacity protected beam. You will get some cracking under service conditions, but you probably are hoping that that's not yielding your reinforcing. And so you're likely going to get cracks a lot smaller than 0.8 mils. If your cracks are smaller than 0.8 mils, the C2 capacity is very conservative. Again, not necessarily a problem. Conservatism is generally good, but a really good thing for you as a designer to be aware of when you're using it. Similarly, let's say we are wanting to strengthen a single-story reinforced concrete frame, and we're wanting to bring the drift limits down, or the drifts down. So we put in a really stiff steel braced frame, and we connect it laterally with post-installed anchors into the original concrete columns. Do we expect in that scenario cracking representative of reinforcing yield in the columns? All right, we've stiffened the system. The columns arguably aren't going to be taken to yield of their reinforcing. The cracks are probably going to be much smaller than 0.8 mils. C2 capacity is conservative. Probably by quite a lot. Again, not necessarily a bad thing, but it's something to keep in mind. Getting a theme here. Pre-stressed beams, right? Reinforced concrete beams fundamentally need to crack so that we engage our reinforcing so they behave as we design them to behave. Pre-stressed beams are fundamentally a different mechanism, right? You're relying on that compression force in the pre-stressed concrete member. We don't expect the same cracking behavior in a pre-stressed member as we do in a reinforced concrete member. Fundamentally, what a C2 capacity is allowing for is that 0.8 mil crack, which we probably don't expect in most scenarios in pre-stressed beams. There are, of course, extreme scenarios that are worth thinking about, right? Positive and negative moment failure in hollow core slabs, you're probably going to get some cracking in those locations. But for the most part, we really don't expect substantial amounts of cracking in most of what we're doing with pre-stressed concrete. It's a different mechanism. Hollow core. Now, there are actually a couple of application examples like this, but this one's a nice one to illustrate it. What I've got there on the top is a screw anchor installed in hollow core through the core. Right? And on the bottom, I've got a through bolt connection, and the arrows are showing how they resist tension and shear in that scenario. In tension, the screw anchor behaves much like a post-installed anchor, right? That load transfer is happening through the threads. The through bolt, in comparison, is really a bearing connection on the top of the hollow core unit. Fundamentally more reliable, does not get designed using a C2 capacity, right? That's just first principles, steel and bearing. If you look at the shear connection, look at the through bolt, we load it in shear underneath the unit. overwhelmingly, the shear resistance is coming from bearing between the steel shank and the unreinforced concrete underneath the core. The screw anchor, or any anchor really, it doesn't actually have to be a screw anchor, exactly the same mechanism. Okay? C2 capacities for that shear loading of an anchor through a core of a whole unit, because you have that offset between the point of resistance, which is a bearing, and the actual post-installed connection, it's just not at all represented by a C2 capacity. Okay, a couple of notes on standards. There are a couple of application standards. The three on the bottom of the screen there definitely have examples, but there might be others as well of ambiguous references around what you should do for use of C1 and C2 capacities in concrete. This can be solved with an overarching statement. Right? Fundamentally, our codes in New Zealand are built with a hierarchy. We have our Building Act, we have our building code, we have our standards. Our standards have a hierarchy. Right? We have loading standards, we have material standards, and then we have specific design standards. The ones at the bottom are all specific design standards. I think those specifically are fire hydrants, bracing, and automated sprinkler systems. Fundamentally, they are subservient to 3101. Right? 3101 requires use of a C2 capacity. Therefore, if you're following a specific design standard, that fundamentally still falls under the 3101 requirements. Okay. If we were to try put a sentence to what we're actually talking about when you look at what a C2 capacity is, a reasonably, sufficiently specific response would be something along the lines of an expected 5th percentile capacity of a post-installed anchor in a reinforced concrete beam outside of the plastic hinge zone in a crack 0.8 mils wide in a 90th percentile earthquake, 90th percentile 475-year return period earthquake in Los Angeles, California, America. If we were to try and be specific about it, that is what a C2 capacity is. That is physically what we are testing when you get a C2 capacity. Okay, back to my timeline. I put this here with a nice question mark. Things happen fairly slowly in our industry, developments in this sort of area, for good reason. I will be very, very surprised if we look back in 10 years and we're doing things the same way we are doing them now. Things will develop. Your voices in the industry will impact the direction that goes, very much so. And on that note, I really want to leave you with a thought. Assessment criteria, whether it is for post-installed anchors or anything, exists or should exist to support you, the designer, to provide you, the designer, with the information that you need to design correctly, safely, and with systems that you understand. It is not there for suppliers to differentiate their products. And I think it is the role of groups like Auckland Structural Group and CSOC to advocate on the side of designers for assessment criteria to reliably move more and more in this direction. Thank you. Any questions on any of that?